much we could say better. Okay, so we're going to start with chapter 11 today, and then maybe by next meeting we will be done with chapter 11. And if you're going to look at the classes that we have, start trying to I already posted there some sort of the first assignment, and I'm going to discuss about that when more people are online. So it's still 2 minutes before our, what we call start time. So if you're going to look at the content here, so the slide is the one that we have right now. It's up there. And then the reviewers, I already, what we call uploaded the correct document. So there are 3 reviewers there for each exam that we're going to have. Now, I don't know if this is a good news or bad news for you. I think Dr. Brenner already told us that he already set the final exam. So just like before, I'll find ways to uh, get over that thing, or at least find a solution. So you're not getting 2 exams on the same day. I'll try to find a solution to that. Okay, maybe similar to what we did last semester. So I have posted the first assignment that I'm going to discuss to you, and what will be its role here in our what we call class. Okay, so we're going to start with the lecture proper. So if you're going to look at this, you might be surprised. Why did we go back to why did we start at chapter 11 and not chapter 1 again? So as I've told you last meeting, Gen Chem 2 is just a continuation of Gen Chem 1. So we will continue what we have started in Gen Chem 2. And I hope that you still remember some of the concepts that we discussed during Gen Chem 1. So if we're going to look at this, the first topic that we have here, you might ask, why did we go right away with this one? So remember, if you have chapter 1, we discuss about solid, liquid, and gas, right? The SLG. Okay, this is not the Trinity of God, the Son, the Lord, and the Ghost. This is what? The solid, the liquid, and the gas. So what do you remember from the solid, liquid, gas? How are we going to differentiate these 3 physical states? There are 2 categories that we use. Do you still remember that? What's that categories that we use?
Volume and shape.
Okay, the shape and the volume. Okay, so if you're going to look at this, if it's a solid, shape and volume are what? What's the letter D here means?
Definite
Define.
shape, definite volume.
Okay, so it's a definite shape and definite volume. Now the liquid, which is the only one that is definite.
Volume.
Okay, so this is the only one that is definite. This one is not definite. Okay, for the gas, both of them are not definite, right? Now, as you can remember, there's a chapter in Gen Chem 1 where we talk about gases. Okay, or if we're going to have some example of a solid, liquid, and gas, so the classic example that I have is just ppf. I just put it like that. So those ppf are things that come out of our body in solid, liquid, and gas form. Okay, I don't want to say anything because some of you might be having your lunch. Okay, so if we're going to look at the molecular structure in terms of how solid, liquid, and gases are arranged, this is how we look at it. So we could say here, gases has what? A lot of space in between them. So because of this, it allows you to put gas in between the space, gas molecules or atoms in between the space. So that is the property of being able to be compressed, or compressibility, or compressible. So we could say gases are compressible fluids. Okay. Now, liquid and solid, because of the small space between them, we could say they are what? Incompressible. Okay. Now, the question that may be asked here, what separate these two, solid and liquid, from the gases? Anyone?
The laws of the gases.
The law of the gases. Okay. Or maybe we go back to this chapter and we go back to the model that they use to describe the behavior of the gas. What's that model? Anyone? What is that model that explains the behavior of the gas in terms of the constant random motion of gas molecule? So that statement says the gas, one of the statement of that model is the gas moves in random motion. Okay, so anyone who can remember what that's model that we use to describe the behavior of the gases? What is this KMT means?
Kinetic molecular theory, I think.
Okay, so the kinetic molecular theory. So the kinetic molecular theory describes the behavior of the gases. It says that the gas is composed of what? Molecules or atoms that are, we could say, in constant random motion. Okay. And if they are what we call in constant random motion, most of them are what? Gases are mostly empty space. Okay. And if you're going to remember, the KMT explain the behavior of the gas. What does the gases have that the liquid and the solid don't have? And we're going to discuss about that today. This is the condition that you have when you become what we call problematic. Okay. You forget about this. What's pressure? P is equals to what? If you recall your Gen Chem 1. Anyone?
Mass.
Before I recall all the A students?
Isn't it temperature over volume?
No. P is equals to what?
R constant times mass times time.
So what is P? You still remember that? What is F over A?
Force over area.
Okay, force over area. And how does the kinetic molecular theory describe pressure? If you're going to recall the KMT, it's described as the molecules hitting the outside walls of the container. Okay, so when they hit that thing, that's the pressure or the results of that heating of the molecules on the walls of the container. That's the pressure that is being exhibited by the gases. So remember the KMT, there are what, 4 or 5 statements that describes the behavior of the gases. Okay, so what we're going to do, what if we're going to apply the kinetic molecular theory in terms of liquid? What if we're going to apply it in terms of solid? Okay, so the difference that they have here, if you're going to look at the physical state, the main difference that they have is just the distance between the molecules. Now, what differentiates the solid and the liquid from the gases is something in the solid and the liquid that hold the molecules together that you cannot see in the gases. Does that make sense? Do you think there's a force that will hold the gases together, especially at this one? They're moving at a random motion. So that means there's no forces that hold the molecules together compared to the one in the liquid, compared to the one in the solid form. And if you're going to look at the title of this chapter, although if we're going to go here, states of matter, liquids and solids, there's an alternative title that you have there. Okay, the so-called IMFA. This is the intermolecular forces. So the intermolecular, by the word intermolecular. So this is the forces between molecules. And we're going to discuss it in this chapter. But I'm just trying to introduce to you, okay, we discussed liquids and solids. How come this is separated from the gas? And the main reason for that is, okay, they have their own intermolecular forces that hold the molecules or atoms together compared to the gases. Now, how are we going to apply the kinetic molecular theory, let's say, in the liquid form? So if you're going to look at the liquid form, the molecules are what? They're close together compared to the gas form. There's little space between them. Okay? Now, what property do you think differentiate the solid and the liquid from this one? If you go back to our introduction, both of these has definite what?
Definite volume.
Volume.
Shape.
Definite volume.
Volume. You don't have definite what we call shape on this liquid. It assumes the shape of the container. But both of them has what we call definite volume. What allowed them to have a definite volume? The intermolecular forces that hold them together. Now, if we're going to look at the liquid, how are we going to apply KMT? Because if you look at the KMT, kinetic molecular theory, what's the main word there? What's the main word in the kinetic molecular theory? Anyone?
Kinetic.
Kinetic. So what does kinetic means?
Energy of movement.
Kinetic has something to do with what?
Movement. Motion.
Motion, movement. Okay. Now, you might ask yourself, wait, it can be applicable to the gases because the gases are mostly moving at random motion. How can it be applicable to the liquid and the solid? Because as I've told you, we're going to use the KMT to describe the liquid molecule and the solid molecule. So if we're going to look at the liquid, as I told you, molecules, there's a space between them. So as much as possible, they still move in a constant random motion, but not as the one that is observed in the gases. There's a limited, we could say, random motion. What allowed them to have this random motion, that's what we call the extra space, the small space between them. Okay, they are more tightly, we could say, packed, less space. But what do you think allowed the liquid to flow? Like if I sip my water here from my mug, the solid flow.
No.
Okay,
No.
so that flow of liquid, that is the movement, that is the random motion that you can observe, although it's not as what we call obvious as your gas. Okay, now we go to the solid. So how do we describe the solid? They are what? Tightly packed. They are arranged in definite order. Okay, and we're going to classify some of the solids also in this chapter. Okay, so if you're going to look at the solid, the particles exist in close contact and do not move about. But how is the movement applicable? There is what we call the term vibration. So what does this vibration means? Okay, so molecules tend to vibrate, or another term that they use there is oscillate. So even though they are in what? Fixed position. Okay, so if you're going to look at this solid state, you can still see the motion of atoms within the molecules. And in fact, there is a great research field known as vibrational spectroscopy. You will know about them when you go to organic chemistry. They call it the IR and the Raman. And usually that is my research field. Okay. So what does the vibrational spectroscopy do? We have the so-called functional group. And each of these functional group, so this is a group of atom. Okay. So they have the so-called vibrational signature. So if they are present, let's say if I'm the water. So if I'm the water, how will I do the movement? My head is the O and my hands are what we call the hydrogen. So I can make the motion like this, which they call symmetrical stretching, or I can make it like this. And this is what they call the asymmetrical stretching. So the OH is just one example of this functional group. And you will be introduced to that when you go to your organic chemistry. Okay, so you can monitor the movement of your solid. It's not only in the solid, it can also be observed in the liquid and the gas. But in the solid, that's the only motion that the molecules has. Okay, so that's how we apply kinetic molecular theory in solid, liquids, and gases. Now, if you're going to look at them, how do you usually transform from solid going to the liquid and then going to the gas? What do you need?
Heat.
Heat. In general, what do you call heat? Heat is part of what?
Energy.
Energy.
Energy. So the removal, okay, or the addition of the heat is the one that transforms from one phase to another. So if you put heat in the solid will melt, okay, to form a liquid. If you add further heat, okay, your liquid will become what we call gas. Now, usually the heat associated here to convert, let's say, 1 mole of solid to 1 mole of liquid is called the heat of fusion. And the heat that is associated to convert liquid to gas, that is called the heat of vaporization. But the process that you have is what? This is solid going to the liquid, that's melting. This is liquid going to the gas, that's vaporization. Now, you can also have what? Solid being converted right away to gas without passing the liquid state. And the process that you have there is sublimation. And if you're going to look at this, the heat associated to it is heat of sublimation. So those heat of sublimation, heat of fusion, heat of vaporization, those are the heat that you need, okay, to convert from one physical state to another. Now, if you're going to remove the heat, you have the reverse reaction. So from liquid, you remove the heat, it will become frozen to become solid. The term that they use there is freezing. If you have a gas, you remove the heat, what you do, it condense or it liquefy and you form the liquid. Now, if you have the gas form going right away to the solid form without passing the liquid state, that's the deposition. So I have a lot of stuff here for a multiple choice question. Okay. Now, the thing that we're going to look is the liquid and the gas phase. So let's say if I put here one with water and I put here one with acetone. So let's say I put 100 ml, each of them. You left the container open. After some time, which one will have less volume? The water or the acetone?
Acetone.
Acetone.
Acetone. Okay? But what if I covered it? After some time, what do you think is the level of the water and the acetone liquid? Or what will be the volume of both the water and the acetone in the container?
Will stay the same.
Okay, they will be the same. Okay, but if you're going to remove that, what we call cover, the acetone will what? Vaporize at a much faster rate compared to the water. So what could be the property that affect that thing? Okay. So if we're going to look at the conversion of the liquid to the gases, it's called vaporization. Now, what happened initially if you just have a liquid? I think I have it here. Your liquid will what? Vaporize to form gas, right? However, since it is covered, what will happen? There will come a time that some of your gases will not, since they were not able to escape because the container is covered, those gases that form, okay, they start to condense, right? So when they start to condense, what happened?
It's going back to liquid.
Some of the gas molecules goes back to the liquid form. And there will come a time that the exchange rate of vaporization and condensation will be the same. And we have here a system of what?
Equilibrium.
Equilibrium. That's the magic word for the course. Okay. Now, as you could see, this can only happen if the container is what? Closed. What happened if the container is open?
The gas will flow out.
Okay. there will be no equilibrium because everything will just be what? What process will just happen?
Vaporization.
It's just vaporization. Okay. So what allow us to have the equilibrium is to make it into a closed system. Because if it's an open system, it's just like the name of a band, a boy band called One Direction process. Okay. So we go now to this concept of vapor pressure. What does this mean? Pressure is just associated with what?
Gas.
Gas. Maybe we could say a gas. Now, if pressure is associated with gas, what does this vapor pressure means? So the main root word there is vapor. So this is the pressure that was formed when you form the gas form. When you have the gas. So it says here, the vapor pressure of a liquid at a particular temperature is the partial pressure of the vapor over the liquid measured at equilibrium. So let's say we have a water sample, or maybe a liquid water here. Okay. Now your liquid at 25 degrees Celsius, what happened? Some of that vaporized. And when the water vaporizes at that particular temperature, the pressure that you have is this one. Now, let's go with the acetone. So, as we have in our previous example, you said acetone will have less volume, okay, if you leave it open compared to water. Why? Why do you say that acetone will have less volume compared to water? What will happen? More liquid, what? Evaporate or vaporize, right? Now, my question is, how do you compare the vapor pressure of the acetone compared to the vapor pressure of water?
The boiling point?
Is it higher, lower, or the same? BP acetone versus BP water. Anyone can answer?
It's higher.
Okay, higher. How the other?
I think it's also higher.
Okay. So as you're going to see, vapor pressure of acetone is higher than vapor pressure of water. Now the question is why? Anyone?
Is it because it has a lower heat of vaporization?
Is it lowest vaporization?
Does it have a lower boiling point than water?
No, we don't go with the boiling point yet.
Okay.
We stick to the example that we have. Why do you think the vapor pressure of the acetone is much higher than the vapor pressure of the water? The answer is also there in your what we call observation. So you said you have what? Less volume of the acetone compared to the volume of the water. So what does it mean? There are more acetone that is in what? Gas form. Does that make sense?
Yes.
If you have less volume of liquid, that means you have more volume of gas. And if you have more volume of gas, that will exert more what?
Pressure.
Pressure. Remember, vapor pressure. It's the pressure that comes from the vapor form of your liquid. So if you have more vapor pressure, if you have more vapor there, that means you have more pressure. So that's why the main reason why the vapor pressure of acetone is higher than the vapor pressure of water is because most of the acetone are in gas form. And if you have gas form, remember, you only exert pressure if you are in the gas form. So the higher is the vapor pressure. So you can now say the vapor pressure of the acetone is higher than the vapor pressure of water, just based on this observation. Now, how are we going to relate now? Let's say we boiled both, okay, the liquid and the acetone. What will happen to the vapor pressure now? Both of their vapor pressure will also increase. So if you're going to look at it, the vapor pressure depends on the liquid, on the temperature. So if you increase the temperature, you also increase the vapor pressure. Okay? So if we're going to look some other liquid, so this is what happened when you change the temperature and the resulting vapor pressure. So as you're going to see here, it's not really a linear relationship, but at least as the temperature increase, let's say here for water, from 20 degrees Celsius, you have a vapor pressure around what? Less than 100. Okay. If you make it to 40, it increases. But this happens to all the liquid here. Now, what information you can get from this data if we're going to look at the different forms of the liquid? If I ask you the question, okay, which has the lowest vapor pressure, or which is the most, we could say highest, or which has the highest vapor pressure, how are we going to look at this one? So if I'm going to compare between water and carbon tetrachloride, which has a higher vapor pressure?
Water.
Carbon tetra.
Hmm?
Isn't it carbon tetrachloride?
So if I'm going to add, let's say at 20 degrees Celsius, which has a higher vapor pressure between carbon tetrachloride and water. So what you do is you go to here and then look at the vapor pressure that you have there. You have here this one compared with what? This one, right? So which one is higher?
Carbon.
The carbon
Tetrachloride.
tetrachloride, right? So that's how you're going to answer questions like that. So if you're asked which is a higher vapor pressure, so you have to look at one temperature and then compare the vapor pressure. So if I'm going to ask you which is the highest vapor pressure among the four liquids, what will be your answer? Those are the type of questions that you can expect in the first exam and the final exam. Or I can make the question, which is the lowest vapor pressure?
Water.
Water.
Yeah, water.
Okay, so which is the highest vapor pressure among the four liquids?
Diethyl.
The diethyl ether. Okay, so that's the information that you can get. So you might just look at this. So maybe the one in the what? How do you see this? The rightmost. That's the one that has the lowest vapor pressure, and the one in the leftmost, that's the one that has the highest vapor pressure. This one is the lowest. And how do you compare them? You just look at the same temperature. So if you're going to look at this, so this is this one here, this one is here, so this one is here, this one is here. Does it make sense?
Yes.
You are going to ask which is the highest vapor pressure, which is the lowest vapor pressure. So all you need to do is find one temperature and then get the vapor pressure of all the liquids that is being compared. And it's much easier for you to answer that question. So do you think you're not going to get the 0? You get at least what, 3 points in your exam if these figures come out? Okay. Now, Although the main figures really tells you the relationship of what? Temperature and vapor pressure. So if you're going to look at that relationship, you could see as this increase, the temperature increases, the vapor pressure also increases. Okay? Now, boiling point. So that's how we now put the boiling point and the vapor pressure. Okay? So boiling point, we could say this is the temperature at which the vapor pressure is equal to the pressure on the liquid. So usually atmospheric temperature. And at these temperatures, the bubbles of gas forms within the liquid. The normal boiling point is measured at 1 atmosphere pressure. So we could say here, this is one way to differentiate vaporization and boiling. In what aspect are they the same? Anyone? In what aspect vaporization is the same as boiling?
They both change liquid to gas.
They both change liquid to gas. Now, in what aspect are they different?
Temperature.
Okay, temperature. If you're going to look at the answer to that question, it's there.
It's not vapor
Usually boiling has this, vaporization don't have this.
and boiling point, the vapor is equal to the pressure. Like
Okay,
the vapor.
you have this bubble. You don't see any bubble when vaporization happens. Because usually vaporization is just a spontaneous process. As long as you put it at room temperature, it will vaporize. Boiling, on the other hand, is, we could say, a forced process. What does it mean? If you put the heat or the energy, you are forcing it to convert from liquid to gas. And usually when you do that, you observe bubbling or the formation of the bubbles. And the way that you do it is you reach the temperature by which it starts to boil. You know, you can have vaporization even though you don't have the boiling point. Vaporization can happen even in a temperature lower than the boiling point. Okay. Another thing that you have to consider here is the atmospheric pressure. So usually you want the boiling point to be the temperature by which the pressure is given. So if the pressure is 1 atmosphere, then you call that a normal boiling point. So what does it mean? Boiling point can change. The temperature of the boiling point can change if you have different what? Pressure. But if you set the pressure at 1 atmosphere, okay, the temperature at which the liquid boils to gas, you call it the normal boiling point. But if you vary, okay, the pressure, you can have different boiling point. Classic example here is this one. You see this? So water boils at 100 degrees Celsius at sea level. What is the atmosphere at sea level? What is the pressure at sea level? Usually
1 atmosphere.
1 atmosphere. Now, as you go up the mountain, let's say in Colorado, okay? What do you call that? The Mile High City? So the elevation is 4,400 meters. What happened to the boiling point of the water? It's 85. Why? What happened to the pressure there?
It decreased.
It decreased. It is less than 1 atmosphere. Okay? Because the relationship of pressure is related to temperature, or vice versa. Temperature decreases when the pressure decreases. So here the boiling point decreases because the atmospheric pressure is down. And if you go to Mount Everest, it went down lower, 71 degrees Celsius, because the pressure is way, way below. Okay? And that is also the concept that we have with the pressure cooker. So what happened with the pressure cooker? When the pressure on the liquid increased, as is in the case with the pressure cooker, the boiling point also increased. So maybe I have some question here. Oh, okay. Okay. So I'm trying to do, because I have a full question. So this is the question that I have. Answer it as soon as possible. Is the rice cooker the same as the pressure cooker? I want to know because every semester I always have the same problem with my student, and because of that I also have to remove the background that I have. So where's the other? Why are the other not participating? Because I'm going to show you the difference between the two. Okay, so I'm going to end the polls. And to the first student who said that they are the same, they're not the same. This is a pressure cooker. Okay, so you close this one, and what happened? You allow it to build pressure while heating it. If you want to release pressure, you're going to press this one. Now, if you are Asian like me, we always have the rice cooker. Okay, so in what ways they are the same? The pressure cooker and the rice cooker. In what way they're the same? Anyone?
They use heat.
They use heat. Okay, but in what way are they different? The pressure cooker, in addition to heat, it has pressure. What do you put in the pressure cooker? Anyone? What do you usually cook in pressure cooker? Now it shows you don't cook.
Soups?
You put meat,
Yeah.
right? To tenderize the meat. So try to put a beef there. Okay? Even if you're going to boil beef for several hours, you still have a hard time eating it. But if you put it in the pressure cooker, it will get what? Soaked, because it will tenderize the meat. Okay? So the same principle is being applied here. If you apply pressure, the boiling point will increase. So if the boiling point will increase, what happened to that? The water, or we could say the temperature will increase. So there's now an elevated, okay, temperature because you have a higher pressure. So that's the application of this concept, the relationship between liquid and vapor pressure. So you see it in the application here in terms of boiling, let's say, water. Okay, so if I ask you, in which what we call location will the egg boil slower, or the time to boil the egg is longer? Is it the one at the sea level, the one in Colorado, or the one in Mount Everest? Okay, so you might say it boils faster here because it's just 71, but for the egg to boil, you need at least the 100 degrees Celsius. Okay, now another thing that you need to know is that this one, the freezing point and the melting point. And again, I have a poll here. So please answer. Crazy chicken. Pollo loco. Loco pollo.
Professor,
Yep.
could you just quickly re-explain the main difference between the rice cooker and the pressure cooker?
The what?
The difference between the rice cooker and the pressure
The
cooker.
rice cooker just use temperature. The pressure cooker, you adjust the pressure so you can go higher than the 100 degrees Celsius that is the boiling point of water. Water is the one that you have there. So you can go over elevated temperature because of the elevated pressure. Okay? Everyone answer? Freezing point is the same as the melting point. Oh no. 80% said they're not the same. They're just the same. What is the freezing point of water? Anyone?
32 degrees Celsius.
Huh? Freezing point of water.
Is it 0 degrees
0
Celsius?
degrees Celsius. What's the melting point of ice?
0 degrees.
Huh? 0 degrees. So those 42 students who said they're not the same, are you now convinced that they're the same? Hello, 42 students. Are you now convinced that they're the same? That the freezing point and the melting point of a substance is the same temperature?
See,
Anyone?
I was thinking Fahrenheit, so I confused it, but yeah.
That was surprising to me. I'm going to get this poll every meeting. So, to convince you that they're the same, so let's look at water. Water is water in liquid form. It's ice in solid form. What's the freezing point of water? 0 degrees, right? So what's the melting point of ice?
0
0
degrees.
degrees, right? So this is the one that convinces you that they're the same. But you know, every semester, I always have this problem. This question came out because of my experience from my previous classes. Okay? So the freezing point is the temperature at which a pure liquid changes to a crystalline solid or freezes. And the melting point is the temperature at which a crystalline solid changes to a liquid or melts. Okay? Now, this is what we call a heating curve. Okay? So what does the heating curve tells us? Okay? The heating curve shows us the relationship between the time when energy was added and the temperature. So what happened here, you add energy and you're going to monitor what happened to the temperature after some time. And since you're adding an energy here, there are changes in terms of what we call the energy. Okay? So for instance here, at the beginning, what do you have? It's all ice. It's all what? Solid. So when you apply heat, what changes in terms of the energy? Is it the kinetic or the potential energy? Which one changes?
Kinetic,
Okay, kinetic. Why?
because the molecules move faster.
Okay, move faster. What's the other reason? Why do you think the kinetic energy is the one that's changing? You look at here. What do we call about the temperature? Temperature is a measure of kinetic energy. So as the temperature increases, what happened to your kinetic energy? Anyone? What happened to your kinetic energy as the temperature increases?
It increases.
Also increase.
Also increase. Now what happened to your potential energy? Anyone?
It's decreasing.
It remains constant. Why? What tells me that it remained constant? Because they are all what? Ice. Which is what? Solid form. So once you reach this one, what point is this one? That's your melting point. So what happened in the melting point? Is the kinetic energy increasing?
No.
Yes or no?
No.
No, because as you're going to see here, it's just a straight line. So that means the temperature remains the same. So that means at this portion, your kinetic energy is
Potential energy. Potential energy is
constant.
increasing.
Okay. Now, what do you think happened to your potential energy? Is the potential energy constant? What happened? Here, your solid starts to become
It increases.
liquid. So in that case, your potential energy increases. And then the process repeats again. Your solid now becomes all liquid. So here is all liquid. So the kinetic energy is the one increasing. The potential energy is constant. And then you come here, what will happen? What point is this one? That is now your boiling point. Okay, so in your boiling point, what happened? Your liquid starts to become
Gas.
So in that case, your kinetic energy will remain constant because you have the same temperature, and your potential energy will increase because the liquid now is converted to gases until it becomes a steam here. Now, if you're going to look at this so-called mirror image of this, that's the one that you're going to do in the experiment. That is what we call the cooling curve. And in that case, you are removing energy. Okay, so it's just showing you the relation here of the energy that is being applied to the temperature and the change in the physical states. So this is the heating curve of water. Okay, so we go back to this concept that I have told you earlier. So the heat associated when you want to convert a solid to a liquid, that's heat of fusion. So if you're going to write the, what do you call this, chemical equations, this is how it looks like. And then the heat of vaporization that you have here, that is the heat associated to vaporize a liquid. Now, as you could see here, why is this higher compared to this one? Anyone wants to make a guess? Anyone? Maybe I'll call those the ones that are typing just emojis in their chat.
It takes more energy to change a solid to a liquid to a gas than a solid to a liquid.
Okay, but why? Why does it take energy to convert liquid to gas compared to solid to liquid? Who's the initiator in that emoji thing? Because I was just surprised, 60 messages.
Because gas doesn't have the definite volume.
The definite volume, definite shape. So the main reason that you already are close to it, the main reason here is what? You're breaking the IMFA here. So it takes a larger energy to break the intermolecular forces that hold the liquid molecule. Okay, here what you do is you're just breaking what holds the solid together to become liquid. You still have the IMFA, but here, okay, for you to make the liquid into gas, you have to break the forces that hold them together. That's why if you're going to look at this, it's around what, 40.7 to 6.01. Now the question that I have here, how are we going to get the heat of sublimation? So if you remember Hess law, how are we going to get this one? Oh, is Ali Raka as the culprit? Hey? So
That's
how
false information.
is the relationship of these two? Ali, what's the
Yes.
relationship of these two? I already put them there in order. So what do I need to put in between these two? If you're listening, I have it here at the beginning. So see how the sublimation and the melting and the vaporization. So this is heat of fusion. This is heat of vaporization. So this is just heat of sublimation. So how will I relate these two to this one? Isn't it just like this? Make sense? The thing that I need here is just, so the heat of sublimation is just the sum of the heat of fusion and the heat of vaporization. Okay? And you could always expect that the heat of sublimation is higher than the heat of fusion and the heat of vaporization. So heat of fusion and heat of vaporization, that's just one property. Okay? So right now, we're talking about the property that you can have for the liquid and the gas. Okay? Now, what did we do now? So remember this. So it's very hard to get a relationship out of this, what we call graph. So what they did, so you're going to look at here, temperature and vapor pressure. So what some people did is the temperature, he converted it to 1 over T. While the pressure, he converted it to ln of P. And he ended up with this relationship. Okay, and if you're going to look at here, water now is in the leftmost, while diethyl ether is in the rightmost. But the property of the vapor pressure is still the same. Okay, water has the lowest vapor pressure among the four liquid. Now, what relates this, what we call to? This is what we call the Clausius-Clapeyron equation. So we could say this is the calculation that you have in this part. So the Clausius-Clapeyron equation describes this graph. And if you're going to look at here, this is how it tells us. The ln of P2 over P1 is just equals to heat of vaporization over R times 1 over T1 minus 1 over T2. And it says here, this equation can be used to find the vapor pressure, the heat of vaporization, or the temperature. Now, the question that we have here is, can we relate this equation to a phenomena that has happened lately? And I think I have a poll here, the last one for today. And I'll give you a specific example on that. I'm going to trace whoever answered the Earth is flat. Somebody answer that thing. Yeah, most likely. Remember, you have what? 5% participation and attendance. It's okay if you guess. Okay? Hopefully you're not the one who says that the earth is flat. Okay? Going once, going twice, done. So most of you answer yes. What is that phenomena? Okay? Anyone? Among the 41 students who said yes, what is that phenomena where this is applicable? It's common in the area of Florida, Texas, the Caribbean. The Caribbean.
Humidity?
Is it humidity?
Hurricanes?
You're close to it because it starts with letter H. Hurricane. Yep. Science is a lie. Oh my God. The hurricane. Okay, here, I'm going to explain to you why science is not a lie. What's the problem with the hurricane that we have lately? Anyone? What's the problem with the hurricane that we have lately? Usually it comes with what? So much flooding. What's the explanation for that? Okay. The Clausius-Clapeyron equation answers that phenomena. Why the hurricane lately has a lot of water with it. For every increase in the temperature, okay, there's a corresponding increase in the vapor pressure of the water by 6%. Now, if there's an increase of 2 degrees Celsius, that means the capacity of the hurricane to bring water with it is around what? 14% much larger. So an increase in the temperature, okay, would result in an increase in the vapor pressure. So vapor pressure is just what? Liquid in the gas form. So the global warming that we have right now results in a much more devastation of hurricanes here in the US, typhoons where I came from, okay? Because there are more waters now that is being converted into gas form and they bring it along, okay, when they have this hurricane and the typhoon. And the Clausius-Clapeyron equation explained that. This just relates that for every increase of temperature, there is a corresponding increase in the vapor pressure of a given liquid. Okay? That's why it's so sad that a lot of people don't believe in science. Okay? We always said that the US is the best, but to tell you frankly, it's not the best country anymore. Because everybody don't believe in science. Okay? What's the classic example that this is not the best country anymore? The pandemic that we have. If we're the best country, how come we have the most number of what we call deaths around the world? Okay? And with regards to what we call the thing that is happening right now, I don't know. But you know, sometimes it's easier for stupid people to create conspiracies compared for the smart people to defend the science that they have. Because scientists itself are what we call talking with one another or what we call exchanging ideas. Sometimes the exchange is not really pleasant, okay, compared to the one that, oh, somebody spoke it in what? YouTube, in the social media, and everybody believes in it. Okay? The only failing that we have in science is most of the smart people are always in doubt that they don't want, okay, to say anything. And most of the idiotic people, they're just full of what? Nonsense. And they are the one who just put all this nonsense on the social media. And this is the reason why celebrities are much more popular than scientists. But the question now, can celebrities help you with the pandemic that we have at this time? Okay? Right now, the thing that we have can only what we call solve with science. everyone is entitled to his own opinion, but not to a fact. That's the thing that we could I could say about the science. Okay, and it's so sad because U.S. is just like of that. I'm sorry to tell you, but the way I look at America right now is not the same when I arrived here. Okay, and it's become now some sort of my advocacy that maybe I'm here to help the people be enlightened of what is happening around. All I can say is there are a lot of idiots that we have here in this country. I don't want to talk political of it, but I'm just trying to explain this to you. These are the types of science that you need to know to explain to those people who are full of nonsense and who believe to people who are also nonsense. Okay? So there's no such thing as lizard people that we have. So the explanation that we have why the hurricanes are so much worse at this time is because we have a higher temperature. So Clausius Clapeyron told us the higher the temperature that they have, the more vapor pressure that we have. So that means the more water it can carry coming from what? Atlantic Ocean going to here. And what's worse, sometimes it just came what? A week after, and one time there's 5 hurricanes at the same time. So it's just getting worse. Okay. So let's try to solve problems like this one. So the vapor pressure of diethyl ether is 439.8 millimeter mercury at 20 degrees Celsius, and the heat of vaporization of ether is 29.2 kilojoules per mole. So what is the vapor pressure of ether at 34 degrees Celsius? So if we're going to look at this, the way that we solve problem here, so we put all the given. So what's the given that we have? Temperature 1, 20 degrees Celsius. Pressure is 439.8 millimeter mercury. And then, so that's P1. Heat of vaporization is given as 29.2 kilojoules per mole. And then B2 is equals to, no, T1, T2. So the question now is B2 or P2. Now, can we predict what will be our P2 with respect to our P1? Can we predict that? What can you say about P2 with respect to P1? Will it be higher, lower, or the same? Before we solve the answer.
Will it be higher?
Okay. So if you're going to look at the Clausius-Clapeyron equation, it says the higher the temperature, the higher is the pressure. So from 20 degrees Celsius to 34, so this expected to be higher. So before we put in place, okay, before we use this equation that we have here, what else do we need to do first? Are we going to use the temperature as degrees, or we have to convert it to Kelvin? Okay. So just like before, you're going to convert it to Kelvin. So if you're going to do that, so 20 degrees Celsius, that will become what? Plus 273, so that's 293 K. And then 34 plus 273, that will become 307. And if I follow the thing, so this is Ln, I don't have the P2, I can just use millimeter mercury. I don't need to convert it to atmosphere. It's fine because If you do that, you maintain the millimeter mercury, your final unit will also be millimeter mercury. So it's okay if I just use millimeter mercury. Okay? So you don't need to convert that to in it. So Ln is an operation that you can find, I think natural number. And the inverse of that, if I'm not mistaken, is E. Okay? So this is equals to the heat of vaporization, which is 29.2. Now this is what? Kilojoules per mole. So you have to be very careful because the one below is 8.314 joules k-mole. You still remember that? So what are we going to do? Maybe you can multiply this by 1,000 joules per kilojoules, and then you're going to put here, you're going to multiply here the 1 over 293K minus 307K. So these are in one, what we call the side. So if you're going to do, you have the Ln here, that's the P2, the 49.8 millimeter mercury. And if you're going to do the operation on this side, what do you get? I think someone has an answer. Okay, so that will be equals to 0.5466. And then what do we do? How do we remove Ln? So it will be P2, 439.8 millimeter mercury, E raised to, right? Am I doing it right? The EX. Did you get it? So what's the value that we have? E to the 0.5466. 1.727. Okay. And if you're going to do P2 equals to 1.727 times 439.8 millimeter mercury, what do you get? What's the final answer? I'm going to put the final answer around here.
760.
Okay, you got around 760 millimeter mercury. Okay. So question. Before we move to the last part, the phase diagram. I multiply it by 100 because it's a kilojoules and I divided it with the joules. Okay. So I have a kilojoules there and the one below is the joules. So the best way to do is convert the kilojoules to joules. So to make them in the same unit. So this is a kilojoules, this is a joule. So when I do it like this, I have the joules there. Okay. So the last part that we have is the so-called phase diagram. So a phase diagram is a graphical way to summarize the condition under which the various states of a substance are stable. Okay. So in the phase diagram, the phases are separated by lines that represent the equilibrium between these phases. And you have there the triple point wherein all three phases exist in equilibrium. So if you have a phase diagram similar to this one, okay? So what do you see in the phase diagram? If you're going to look at the one that we discussed right now, temperature versus pressure. And what you do, what can you say in the phase diagram is at a certain temperature and pressure, you could see what is the phase of a given compound. So this is the phase diagram of water. Okay. So what are the other information that you can see here? So you can see here the transformation from an initial phase to another. So let's say you have a temperature from here going here. Now, does this make sense? From here going here, there's an increase in the temperature. Okay. So if we're going to look at this, so this is the solid phase, this is the liquid phase, and this is the gas phase. So the 1 atmosphere pressure that we have here, if we're going to look at here, so this is your what? What do you call this point here? Normal boiling point. And then you have this what we call triple point. So the triple point is where the three physical states exist in equilibrium. So for water, it's at 0.01 degrees Celsius and 0.0063 atmosphere. And then you might ask yourself, what about this one? What do you call this point? So that is your critical point. So the critical point, okay, that's where you cannot distinguish whether your sample is a liquid or a gas. They exist in what we call a supercritical fluid state. And there's an application for that. Okay, so what other information that we can get from the phase diagram? The phase diagram can tell us why your carbon dioxide don't exist as liquid in atmospheric form. What's the other name of CO2? Anyone? What's the other term that we use for CO2?
Carbon dioxide.
Why did we call it dry ice? Is it CO2 also known as dry ice?
Yes.
So why did we call it a dry ice? The obvious answer, because it's not liquid. It doesn't form into a liquid, and the phase diagram tells us why. Look, at 1 atmosphere pressure, that's the condition that we have, your carbon dioxide can either be a solid or a gas. So that means your CO2 doesn't dissolve. It doesn't melt. It what? Sublimes. And the phase diagram tells us that. If you're going to look at this, at atmospheric pressure, it can either exist either as a solid or a gas. Does that make sense? And one thing that I want you to observe here, why is the curve here between the solid and liquid like this one compared to the water that you have here? And that will explain to you, okay, when we finish the chapter next week. Now, there's another term here. We have this phase diagram that we have here. So this is what? This is for sulfur. Now, how is it different from the previous one? Because as you could see here, there's two solid forms. You have the rhombic form and the monoclinic form, and both of them are solid. and then you have a liquid form and the gas form. So what does this tells us? There are some points that you have here, several points. You have what? 3 triple points. But the question that I have now, which is the true triple point? Which is the true triple point here? 1, 2, or 3? Anyone? The true triple point is the one where the 3 physical states exist. So in this case of sulfur, which is the true triple point? Is it 0.1, 0.2, or 0.3? Okay. So if you're going to look at this is solid, this is solid. So that's the one that you have here, and that's the one that you have here. So the true triple point here is this one. You have a solid from here, a liquid from here, and a gas from here. Now, this is also the explanation now, the one that I told you before, why Napoleon lost the war. Okay? And why did Napoleon lose the war? Because of Russia. Russia. Okay? But what's the main thing that make him lose the war? So he won the battle in the pyramid using science, but he lost the war with Russia by science also, specifically chemistry. And the main culprit that they have there is this, the button. Why? Why the button? Button before is made up of what? The buttons of the grenadier before is made up of what?
Metal.
What made up this material? The sardines can. What is the material of the can?
Tin.
Tin. So they found out tin has 2 solid form. One of them is unstable at cold temperature. And I have a video to show you of why Napoleon lost the war. So this is what we call the gray tin. So this is how it becomes brittle after 20-hour exposure at -40 degrees Celsius. So what do you think happened to his army during that brutal winter campaign? Okay, so I'm just showing you there that there are different physical form. Okay.
What could you do with a metal 3D printer? Introducing the metal.
Okay. So what I just shown you is at different temperature, the metal tin can disintegrate. And they said that that's one of the reasons why he lost the campaign, a deteriorating environmental condition. And if you're going to explain it in terms of science, it makes sense. Because what does it mean? The grenadier uniforms that his army has was already what? Falling apart during the Russian winter, and everyone is trying to keep cold while they're what? Sitting ducks of the Russian army. Because the Russian are what? Used to their cold environment. Okay? So we will continue and finish what we call chapter 11 next meeting. And I posted an assignment there. So the way that I want the assignment to do is some sort of an insurance in case you mess up your exam. And I can assure you, you will mess up your exam. That's why I put the insurance there. So what does it mean? I'm not going to make quiz. So I would suggest you submit that on the deadline. And then what we're going to do, maybe get the top 10 highest score of this assignment that you have. I have to grade them, but I'm going to make it easier for my part to grade them. So it's just like an all or nothing thing. So whenever you submit that assignment, make sure that's the final answer. Okay, you get the correct answer. Okay, because what they do, if the answer is wrong, I might mark you wrong right away. Because what we're going to do, the top 10 scores of that, okay, will constitute an exam that will replace the lowest exam. Okay, that's my insurance that I have for this semester, and I would suggest do it. Okay, for those of you who are taking it with me for the first time, I just say do what I said. Okay, because the old students that I have before knows what it means. Okay, so don't wait for the catastrophe in terms of the exam results to happen. Just do what you can do at the start. Okay, I'm not going to give you any quizzes. The only quiz that we have is just to prepare you for the exam, but that's it. So the only alternative that I have that will serve as my insurance are those assignments. And at the minimum, you will have one. So the assignment question has not covered the topic that we have right now. Okay, but you can start looking at it. Anyway, the deadline is just maybe next week. Okay, we still meet for another what we call meeting for to finish chapter 11. So question, because I have to leave, it's 1:34 to pick up my daughter.
All good.
Okay, so if you have any question, feel free to email me. Okay, and I'll try to answer it right away by email. And I'm going to post what we call the link for this thing. So I might just put it in the YouTube video channel that I have, because I'm not sure they may implement the 15 days. After 15 days, you lose the recording in the cloud. Okay? So have a nice weekend. See you on Tuesday.
Okay,
Thank you.
Got it. Thank you, Professor.
Thank
Thank
you.
you, Professor.
Hi.
Thank you, Professor.